Most people enter this field with a strong grasp of textbook theory. You understand how electricity flows in a circuit, and you can solve for voltage and current on a clean, quiet whiteboard. But physical power lines don't exist in a quiet room. They have to survive 80-mile-per-hour winds, heavy layers of ice, and steep, rocky terrain that makes construction a constant challenge. For decades, engineers tried to manage these variables using flat paper maps and manual math. But when you are designing across hundreds of miles of changing landscape, those traditional methods struggle to account for the sheer complexity of the real world. Engineers solve this using a specialized software called PLS CADD. It functions as a massive, real-time physics engine built specifically to simulate the behavior of the electric grid. This allows designers to test how a virtual power line handles environmental stress before a single crew member ever heads out to the field.
Designing a reliable line begins with capturing the exact, unyielding landscape of the project area. Surveyors fly over the route using LiDAR, a technology that uses lasers to map every tree, hill, and building with incredible precision. That laser data is used to create what you see here, a perfect three-dimensional digital twin of the environment. Engineers use this digital model to see exactly where to place towers, ensuring they avoid obstacles and stay stable on uneven ground. By building on real-world data, companies can spot geographical problems on a computer screen, rather than discovering them halfway through a multi-million-dollar construction project. Once towers are set, we analyze wire behavior, a physics balance of sag and tension. During heat waves, expanding metal sags dangerously close to the ground. In ice storms, cold shrinks the wire, adding massive tension that can actually snap towers. The software calculates these climate effects automatically. It runs simulations for heat, wind, and ice to ensure the structure stays within its breaking point. Mastering these simulations is the only way to guarantee a line will stay up and stay safe through decades of extreme weather. In the traditional workflow, surveyors and engineers often worked in separate silos. If the terrain changed, every single person had to manually restart their portion of the math. This software acts as a central hub, merging every discipline into one interconnected 3D environment. If an engineer drags a tower to avoid an obstacle, the rest of the physical design reacts instantly. The software triggers a chain reaction. It recalculates wire tension, checks ground clearance, updates the parts list, and redraws blueprints automatically. Without this, an engineer would have to manually update hundreds of separate drawings and double-check thousands of individual math equations by hand. By replacing that mountain of repetitive paperwork with a single click, the time spent on drafting drops by 95%. Because this physics engine is so complex, you really can't figure it out through trial and error while you're on the clock at a new job. And it is the industry standard. It's used by over 1,600 organizations in more than 100 countries to design our power grids. Major engineering firms like Burns and McDonnell look specifically for engineers who are proficient in this software to lead their largest infrastructure projects. For a junior engineer, having this skill on a resume is a clear differentiator. It shows you know how to apply engineering principles to the actual tools used in the real world. Take the course to move beyond the textbook and learn the actual tools used to build the high-voltage lines we see every day.